Okay, so I read the whole chapter for the first time, so I might be a bit blur when it comes to some of these subtopics. But even though nitrogen is only 20% in the exam paper, it still worth a lot for me. And I think that if you know how to do this chapter, it should be 20 marks free. So yeah, you should be able to know what the basic of nitrogen is. Okay, so the physical properties of nitrogen are it is colorless, odorless, cannot dissolve in water. I mean, it can dissolve, but very hard to dissolve, and it has a very low boiling. No, it's a very low boiling point and a very low freezing point. So these are the temperatures as standard atmospheric pressure. Um, chemical properties in for chemical properties in gas. It has 3 bonds, so it's like this. So that means it is very strong. It is very stable. It's hard to break out. Since it's hard to break out, it doesn't really react much. So it's mostly inactive. However, it does react with some metals to produce nitrites, and it reacts with, I think, oxygen and hydrogen to produce certain types of nitrogen things, like I think it was ammonia and nitrogen monoxide. But again, I don't think that will much come out in the exam because there's only a few spots for nitrogen questions to come out. Preparation of nitrogen gas. There are a few ways. Number one is if you have liquefied air, which is you compress the air and then it becomes liquid. If you compress the air and then try and increase the temperature slowly and slowly, you will be able to take out all of the other impurities, because there are the main component of air is nitrogen and oxygen. But since since nitrogen has a lower boiling point than oxygen does, if I heat up nitrogen, if I heat up the air slowly and slowly, the liquefied air, I mean, if I heat it up slowly, the first gas that will come out is hydrogen gas. So I can just leave it at there, and nitrogen gas will continue coming out. There won't be any oxygen gas coming out because the temperature is not low enough for it to become gas as well. Like what I mean is, I believe oxygen is -183 and it's -19 something, 196 I think. So if I were to heat it up to -190, only nitrogen will become gas. Oxygen will stay as liquid. So that's how you prepare N2 using liquefied air. The next one is reacting. I believe it's reacting ammonium salts and a nitrite salt, or in this case it's sodium nitrite and ammonium chloride react to you heat them out together. They decompose to become sodium chloride, water, and ammonia and nitrogen gas. Thirdly, if you were to let I think you have to heat this up as well. I forgot already. If I remember correctly, to heat it up, or it's already heated up. So 3CuO. If you let ammonia gas go through that CuO, the copper oxide, the ammonia will react with that oxygen with that oxygen in the copper oxide, and then it will become 3Cu plus 3H2O plus N2. Now, because this one is prepared through a tube, so I believe, if I remember correctly, if you want to collect only nitrogen gas, you need to I think this is G. If you wanna prepare it if you wanna get the gas only nitrogen gas, you need to dry out the thing. I forgot how you dry it out. It's like you use another drying agent to dry out the water, so the only thing you'll get in the end is nitrogen gas. For this one, since it's in a solution, but nitrogen is less dense than water, which means that nitrogen will end up slowly going up. So the way you want to collect nitrogen gas is you need to use water displacement method. And water displacement method, I forgot the exact way to set it up, but I just know that according to the book, if you want to collect nitrogen gas here, you need to use water displacement method. Let me see if it's in the textbook. I don't think it says so. Yeah, it doesn't say so. Okay, anyway, you need to know that you need to collect it using water displacement method. You can Google more about what this displacement method if you want. What can you use nitrogen gas for? You use nitrogen gas to create pure ammonia gas and nitric acid. Why? You'll know soon. Next, if you were to have liquid nitrogen, um, it will create a very low temperature area. Why? Because when liquid nitrogen tries to vaporize, it has to absorb heat. Since it absorbs heat, this triple bond that we have here, the triple bond is very strong. So you need a lot of heat to actually break the bond. Because of that, I believe that's how it works out. They have a very strong bond, and to break that bond, you need to absorb a lot of heat. Since it absorbs a lot of heat, it creates a very cold area around it because all the heat there is gone. So you can use this for medicine and to trigger superconductors. Medicine is called a cryogen. I forgot what does it actually do, but it can also be used as a cryo anesthetic, which is basically anesthetic. And then a superconductor. Superconductor means there is no resistance when conducting electricity. So this liquid nitrogen makes the temperature low enough so you can trigger that superconductivity. Because if you don't trigger it low enough, there will still be resistance. Now, the types of nitrogen oxides. The first one is nitrogen monoxide. Nitrogen monoxide has no color, colorless, odorless, and it is toxic. So be careful around it. The way you get nitrogen monoxide is by reacting solid copper with nitric acid. So when you react solid copper with nitric acid, you get water, copper nitrate, and also nitrogen monoxide in gas form. Nitrogen monoxide does not dissolve easily, nor does it react with water. So you can take it out using water displacement method as well. And if it's in air, if it's exposed in air, it will readily react with the oxygen to turn into nitrogen dioxide, which is what we're going to talk about next. Nitrogen dioxide is toxic as well, but this time you can see the color. It is reddish brown, and you can also see the odor, the smell of the odor. It is a very irritating smell, so I'll just call it. It smells bad. So it smells bad, and it has a reddish brown color. So the reactions involving nitrogen dioxide include: if you were to expose it in with water, or in the air, I think. Yeah, if you expose it, it will turn into nitric acid and nitrous acid. So yeah, try not if you wait. Let me just see what it says here again. Oh yeah, I'm gonna look here first because yeah. So this reaction, the one involving copper, I believe here. Oh, this is another one. But they're both similar. Okay. So in the lab, copper is generally used to react with concentrated nitric acid to prepare nitrogen dioxide. So the difference between copper reacting with wait, let me just go out. The difference between this and the one in here is that if you want to produce nitrogen monoxide, you want to react it with dilute nitric acid. If you want nitrogen dioxide, you need to react it with concentrated nitric acid. Why is that so? Because it depends on the content of oxygen. If the copper feels like there's too much oxygen in the reaction, it will cause the nitrogen to combine with two oxygen molecules atoms. So it becomes NO2 instead of NO. So it depends on the concentration of the acid. And also because nitrogen dioxide is soluble in water. Oh wait, for nitrogen monoxide, since it doesn't dissolve easily, you can use the I think it was water displacement method. I forgot the actual. I mean, I don't know the actual method, but theoretically you can use water displacement But nitrogen dioxide is soluble in water, so you cannot use what you cannot use that. You need to use condensation method. What is condensation method? You react the thing with water. So when you prepare this in the lab, when you prepare a nitrogen gas in the lab, nitrogen dioxide gas in the lab, um, you do not want it to react with water because I mentioned here earlier, this reaction here, 2NO2 plus H2O becomes HNO3 plus HNO2. Since it readily reacts with since it dissolves in water, you do not want your water to turn into acids. So you need to use condensation method to dry out the thing, so it becomes nitrogen dioxide. I believe this is how it's done, this way. So what happens is the nitric acid falls in here. It reacts with the copper powder, so it produces copper nitrate and releases nitrogen gas. The nitrogen gas goes through here, and you can see that there's this ice and salt. So yeah, I forgot. I'm not so sure what the ice and salt does. I forgot. I mean, I'm not so sure on why you need ice and salt, but it's something to do with this condensation method. Wait, I think it makes sense now. Okay, normally if you're in the sky, right, the cooler it is, and then and then water will condense and turn into water vapor will become liquid, so it'll become water. If you get what I mean lah. Condensation method is you see that okay, wait, never mind. I just realized the water stays here. So when you want to collect nitrogen dioxide, you want to do it in this way so that only the gas goes up. So only the gas goes up. The water and the copper nitrate stays here. The gas goes up, goes to the tube. This ice and salt is to reduce the temperature of nitrogen dioxide so that it becomes a liquid, and this is why you see this color here. Even though it's a gas, you can make it into a liquid by cooling it. Nitrate salts of heavier metals such as lead 2 nitrate can also be used in preparing nitrogen dioxide. Okay, I don't think we need to know much about that. Next, dinitrogen monoxide, N2O. The only thing that they mention is how it's prepared, which is decomposing ammonium nitrate. Then it'll turn into water and laughing gas. Yeah, laughing gas. The nitrogen monoxide is also called laughing gas because when you inhale it, you will feel funny inside. So it's called laughing gas because it makes you laugh for some reason. So this can be used to become an anesthetic. I believe this is the weird smell that makes it funny. It's actually a kind of sweet smell, but it feels very weird. But other than that, it's just colorless, it's inactive, and it does dissolve a bit in water, but not as much as NO2 does, I think. And if you were to heat up laughing gas at a high temperature, you can decompose it into nitrogen gas and oxygen gas. There are also a lot of other nitrogen oxides, but what is the main thing that they cause? What is the main thing that they cause? The main causes are acid rain and photochemical smog. So photochemical smog happens because nitrogen causes the oxygen to do some weird ass reactions, and they will form ozone. Ozone is where your haze comes from. And this ozone actually produces photochemical smog. So it will harm your eyes, it will harm your health, and it will also harm plant growth. For acid rain, it's different. What happens is, this nitrogen oxide goes out, it gets released. There are a lot of water vapor in the air. Then you have to remember, if you were to react with water, it will turn into nitric acid and nitrous acid. These two are acidic, and that is why it's called acid rain. I forgot to mention one thing. If you were to react nitrogen dioxide with alkalis, you will get a nitrate salt, which is NO3 at the end, a nitrite salt with NO2 at the end, and water. And lastly, if you were to cool it down to a certain temperature, you can turn nitrogen dioxide gas into dinitrogen tetraoxide. But that isn't that important. Now we're gonna go through nitric acid in general. Nitric acid is colorless, but it smells bad. Its chemical properties, its main chemical property, it says it's its physical property, but it's mentioned in the chemical property as well. Nitric acid is volatile, which means that it will easily undergo chemical reaction to form oxygen gas, water, and nitrogen dioxide. In other words, it evaporates easily. It easily decomposes. So that is why you need to store it in brown reagent bottles. Why? There are two reasons. Number one, this thing is sensitive to light. Number two, this thing is sensitive to heat. So if it's hotter, it becomes a faster decomposition. So you want to store it in brown reagent bottles and as well as cool areas. Why a brown reagent bottle? Because it's harder for light to pass through. Why a cool area? Because you don't want it to have a high enough temperature to decompose. Nitric acid is a quite strong acid, and of course it turns blue litmus paper red. If you were to combine nitric acid with carbonate salt, it creates carbon dioxide, but I don't think it's that important. And lastly, this is an acid, it can react with alkali to neutralize and produce salt and water. Now, this is the important part, aqua regia. Aqua regia is emphasized a lot by teacher. You have to know the ratio as well, 1 to 3. What are the two things? Concentrated HNO3 and also HCl. This ratio of 1 to 3 is somehow the perfect formula, and what it causes is this special acid, aqua regia, is very, very, very strong. It's so strong that it reacts with gold. Gold does not react usually. Also, nitric acid is a good oxidizing agent. That means that when nitric acid reacts with certain substances, it undergoes reduction. The nitrogen in HNO3 undergoes reduction. And it oxidizes other substances. So it's a good oxidizing agent. Here are the examples. Yeah, here are the examples. I'm going to read them myself as well. I believe we saw these two already just now. Yeah, we saw these two just now with the copper. And then there's another one with carbon. Now, here's the interesting part. The more dilute nitric acid is, and the more active the metal, the lower the oxidation number of the nitrogen in the compound from which nitric acid is reduced to. So that means the more dilute nitric acid is, and the more active the metal is, what this causes is, it causes the oxidation to be even stronger. So it causes the reduction of nitrogen to be even stronger. So for example, here nitrogen is +5, and here it is here is +5 still, but here is +4, if I'm not wrong. Here is +5, over here it becomes +2. So you see that in diluted solutions, it boils from 5 to 2, so it's a bigger drop in oxidation number. But in concentrated solutions, it's from 5 to 4 only. So that means the more dilute the nitric acid is, the lower the oxidation number. Also, at room temperature, concentrated nitric acid can passivate the surfaces of iron and aluminium to form densely packed oxide films that prevent the inner parts of the metals from further reacting with acids. What that means is, if it were to react, if NaCl3 were to react with iron, it will create this weird layer up here, passivate. And what this layer does is, it protects the inner part. Yeah, it protects the inner part of the metal from further reacting with acids, so it will not dissolve as much. It's like normally, if you were to dissolve an acid in a metal in acid, the whole thing will eventually go away. But in nitric acid with metals, it will instead form a layer around here. And then what it does is the inside does not get dissolved. How do you prepare nitrogen dioxide? And I mean not nitrogen dioxide, nitric acid. There are always two ways to prepare. One is lab, one is industrial. For lab, you react sulfuric acid concentrated sulfuric acid with sodium nitrate. So you'll produce, I don't know what this is called, and HNO3. And then industrially, we call it the Ostwald process. So the Ostwald process is quite complicated. So wait, let me see. At first, nitrogen monoxide is produced by reacting ammonia gas with oxygen under the action of catalyst. The catalyst is a platinum rhodium alloy. So it does its own magic, and what it does is first of all, ammonia gas reacts with oxygen to produce nitrogen monoxide and water. But not water vapor, because it's very hot. So it cannot be liquefied water because it's too hot. So it becomes water vapor. After that, the nitrogen monoxide moves here, and it is further oxidized to become nitrogen dioxide. And then where did this water go? The water ends up if I'm not wrong, the water should end up going here, and it becomes liquefied. Then after it becomes liquefied, the nitrogen dioxide that was just produced, it will go into it will become this. Yeah, it will react with the water that from here to produce nitric acid and nitrous acid. So remember, we're only collecting nitric acid, so the nitric acid is collected. So you have one here. This nitrous acid, it goes back. It doesn't go back. It reacts further. It decomposes into nitrogen monoxide, nitric acid, and water. So this nitric acid, this is the one produced. The water goes back here. Nitrogen monoxide goes back here. So this nitrogen monoxide continues, goes back, and it becomes NO2. The NO2 reacts with the water from here, and also the water from here, to produce more HNO3 and HNO2. Then this HNO2 goes back, produces more NO, more HNO3, more H2O. The H2O gets used here again. The NO gets used here again. It produces this, and it repeats and repeats and repeats. So the summary of these two together is this: 3NO2 plus H2O becomes 2HNO3 plus NO. Why? Let's not talk about it. Okay, I think there's another image down here on how it looks like in preparation. Let me see. Okay, it can be seen from the equation of the reaction that only 2/3 of the nitrogen dioxide is actually converted into nitric acid. That means that if there are 3 NO2, you only get 2 HNO3. So that's not good enough. So where do the others go? As I said earlier, the anode as I said earlier, no, not necessarily earlier. When there's that extra NO2, the NO2 goes back into nitrogen monoxide. And that's because there is a lack of oxygen inside. If you okay. 3NO2 and 2HNO3. You can see that there is 3N and 2N. So there is one nitrogen atom left. Right. And that one nitrogen atom, and there's only one oxygen left. So wait, is there even one oxygen left? Okay, there's not anymore. But since there is less oxygen now, this NO2 will become NO. Because remember, and not because of that. Because remember, in this reaction, this one, let me just see where it is. Here, 2HNO3 plus 1 NO. You see that with this 1 NO, the 1 NO, as I said, goes back into here, and it reacts with oxygen again. So that is why you need to add oxygen into the thing. You have to replenish some air. You have to add back oxygen inside, because you need to make sure that this excess nitrogen monoxide reacts again to produce more nitrogen dioxide, and it causes that whole loop again, which looks very confusing. So yeah, 3 nitrogen dioxide produces 2 nitric acid. That one remaining nitrogen monoxide, what happens to it is it goes back, and then you have to add more oxygen gas, so it'll react and it'll produce nitrogen dioxide again, and then it'll continue the process. Yeah, these are basically the reactions that I wrote. It's from the other page. You can see it from the other page. And then here, after the whole thing ends, there is definitely going to be some excess nitrogen monoxide and nitrogen dioxide gas. And remember, they're both toxic, so they are both pollutive. They are both cause pollution. So to neutralize it, to make it not toxic, it will go into the alkali absorption power, which is 2NO plus NO2 becomes 2NaOH plus 2NaOH becomes 2NaNO2 plus H2O. I don't know if you have to write this, but this is from teacher's notes, so I guess it's important. Nitrate salts. Nitrate salts are salts which have NO3. So it's something NO3. For example, sodium carbonate, sodium nitrate, calcium nitrate, ammonium nitrate. The main takeaway from nitrate salts are they are all soluble and they are also all deliquescent. What that means is they all dissolve in water, but they dissolve in water so much that every time they are exposed to air, they will immediately take the water away so that they become liquefied. So they like water a lot. Because of this, it's very unstable, and not because of that, it's also very unstable. And if you were to heat it up, it will release oxygen gas. But when you lose oxygen gas, when you lose oxygen gas, it becomes like this. So since nitrogen goes from +5 to +2, it is reduced. So it is a very good oxidizing agent because all other substances get oxidized while nitrogen gets reduced. All nitrate salts, they have the same they have one similar product, oxygen gas, but then they produce different products. Some have for example, for active metal, you need to heat it up, and then it will produce solid. For less active metal, you have to heat it up, and then what it will do is it will produce metal oxide, nitrogen dioxide, and oxygen gas. For here, you heat it up and it'll produce a nitrite, NO2. For here, it'll produce a metal oxide, nitrogen dioxide, and oxygen. For inactive metals, it will produce a pure solid because it doesn't like reacting with oxygen, nitrogen dioxide, and also oxygen gas. Some salts mentioned in the book include number 1 is KNO3, which is potassium nitrate. It is the main composition of black powder, which is used for mining and fireworks. This is how potassium nitrate is used to prepare black powder. Ammonium nitrate, we are going to talk more about ammonium nitrate later, but it is mainly a fertilizer. Not talk more about ammonium nitrate, more about ammonium in general. So it is used as a fertilizer, and you can make vitamin B out of it. And remember that if you decompose ammonium nitrate, you can create laughing gas. Okay, so test for nitrate salts. There is a way to test for nitrate salts. So if you want to detect whether it has presence of nitrate ion, first of all, you have to react with concentrated sulfuric acid. And what it does is it will form this nitric acid here. This HSO4 thing, it depends on what it is. It will form I forgot what it's called, the hydrosulfate. I think it's hydrosulfate, but that doesn't matter. The main product here is the nitric acid. So if you react your nitrate salt with concentrated H2SO4, it will produce HNO3. This HNO3 will then react with iron 2 sulfate and iron 2 sulfate. And since iron 2 sulfate, 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 and since iron 2 And since this is all happening in a test tube, right? So what happens is, first you have, I believe it is H2SO4. Yeah, you have H2SO4, H2SO4 and and NO3 salt. So it will dissolve into here, and then you add water to make it aqueous, and then after that, it will keep reacting with this because it's still in the solution. You actually dip this iron 2 sulfate into the solution. It still has H2SO4. So that's why H2SO4 continues reacting. It will produce Fe3SO4, water, and then nitrogen monoxide. And then remember that if you were to react nitrogen monoxide, actually no, not remember. Nitrogen monoxide, if you react it with iron 2 sulfate again, it will produce this brown ring. This is FeSO4.NO. This will form a brown ring. I forgot the actual name for this compound, but we call it the brown ring. So what this means is remember, H2SO4, HNO3, NO3 salt, and FeSO4 are all added together. So what happens here is the H2SO4, the H2SO4 reacts with the nitrogen nitrate salt. It will produce HNO3. The HNO3 reacts with this dipped in FeSO4. It will produce nitrogen monoxide. And then there is going to still be some FeSO4 in here. So if you put more FeSO4 in here, this nitrogen monoxide will react with the FeSO4, and then you'll see some brown ring around it. Something brown will appear. That's the brown ring. Okay, nitrogen cycle. I would love to mention this, but I really don't want to look at this book. I don't want to look at this chapter. So I have a feeling, I don't know. Teacher told us that we already learned it in bio class, but I assume she said that because it's not coming out in exam. So yeah, we haven't learned it yet actually. She expected the teacher to teach us, but I think she knows. So I don't think she is going to put this in exam. I hope at least. If she does put it in an exam, I will cry inside. Okay, second last is ammonia. So ammonia is NH3. You normally find it in proteins and urea. There are a lot of functions of ammonia. You can make fertilizers, nitric acid, ammonium salt, soda ash. It can be used as a solvent. It can be used as a refrigerant. It also can be used as organic synthesis, or it can be used for organic synthesis for like plastic and dyes, for example. The physical properties of ammonia is it's colorless. It has an irritating smell. It is less dense than air. What this means is if we were to put air and ammonia together, here will be ammonia and here will be air. So there will be two different layers. But the main part is ammonia is very easily liquefied. That means if you were to compress it, it will easily turn into a liquid. Why? Because it's very easy to form hydrogen bonds between the ammonia. And these hydrogen bonds are very, very, very strong. And because they're very, very, very strong, if you were to try and turn it back into gas, you need to break out the bonds first. So it will absorb a lot of heat. So since it absorbs a lot of heat, the surrounding will be cold. So it can become a refrigerant as well. Again, be careful when you're dealing with nitrogen stuff. It is very irritative to the mucous membrane of your nose, your mouth, your ears. So if you feel very uneasy in your face, it's probably because you're handling ammonia. How about the chemical properties of ammonia? It is very soluble in water. It reacts with water to form I forgot what the actual name is. Oh, it forms ammonia monohydrate. What that means is ammonia with one hydrogen, with one water molecule together with it. But this thing is very unstable, so it can always become it can always decompose back into ammonia and water. And then not only does NH3 barely react and have a tough time becoming NH3.H2O, but also only 1% of it actually ionizes. So it ionizes to become ammonium ions and hydroxide ions. And again, it's very weak, so it's interchangeable. So we call it a weak base because it has it barely does anything. But it still turns phenolphthalein pink. It's still a base. So it still turns phenolphthalein pink. So since we have OH minus here, we can conclude that ammonia solution is basic. Since it's basic ammonia solution can react with acids to form ammonium salts. And bases can also react with salts to produce salt and another base and another salt, if I remember correctly. So also, ammonium has reducing power because same thing again. It's something to do with this nitrogen. The nitrogen is going to reduce. Since it's going to reduce, it's terbalik this time. Is it terbalik? Let me see. So here is +3, here is +2. Let me see if I wrote it correctly. Okay, I think this one is different. For this one, here's +3. Oh wait, no, I get it ready. I got confused because it's at the front. But H is always +1. So according to the oxidation number, nitrogen here will be -3. So -3 becomes +2. That means it gains electrons, so it gets oxidized. So it has reducing power because it oxidizes itself to reduce other elements. So the example that they give here is this, where ammonia reacts with oxygen gas to produce nitrogen monoxide and water. But also, remember the reaction just now that I mentioned earlier. Copper oxide, if you let ammonia gas pass through it, it will form water, nitrogen gas, and copper. How do you prepare ammonia? In the lab, you just add any ammonium salt with a base. For example, here ammonium chloride and a base, which is calcium hydroxide. It will form a solid. Was it solid? I think it's aqueous. Yeah, it should be aqueous because what happens is it forms water and calcium chloride, and these are together, and then it also forms NH3. NH3 is a gas, so it will. If you look at the book, actually wait, I'm not so sure. Oh wait, it's heated up. Since it's heated up, it's heated up. So it produces solid. It is solid, and then it also produces water gas, water vapor, and NH3. So since water and NH3 are together, if you want to collect ammonia gas, you need a drying agent. You need to dry out the water, but you need to be careful in selecting your drying agent. If you were to select H2SO4, concentrated sulfuric acid, or CaCl2, and hydroCaCl2. Why can't we use those? Because we can use those because these two react with ammonium salts. What this means is remember that ammonium salts reacts with salt to produce base and salt, while ammonium salt reacts with acid to produce salt and water. This is an acid and this is a salt. So it will react again. We want to collect ammonium gas. We do not want it to react again. So you do not want to use these two as your drying agent. So the drying agent in this case is soda lime. Soda lime is, what was it again? I think it was not CaOH2. I believe it's NaOH. I forgot already. Yeah, I think it's NaOH. So why? Because it is a base. Bases do not react with bases. So when the ammonia gas passes through it, it will not react with it, but the water does. Another way to produce in the lab is by heating ammonia solution, which is like you have ammonia solution, NH3.H2O, and then you heat it up, and then you get ammonia gas. But that's a bit too easy. Okay, industrially, we have the Heber process. So the Heber process, this thing is very, very, very popular. What it does is you react nitrogen gas and hydrogen gas together. So N2 plus 3H2, you need a very high temperature and a very high pressure. It has this very weird thing here to pressure it to increase its temperature, and it will produce ammonium gas. If you want to turn it back into nitrogen gas and hydrogen gas, you can use a catalyst such as red hot iron. So how the Heber production goes is N2 and H2 come in here, it will go into the compressor. This compressor turns it into this compressor turns it into liquid, and that is because you want to make it under. No, I don't know if it turns it into a liquid exactly, but it does create a very high pressure. So the compressor creates high pressure. It will go into this iron powder. This is one of the catalysts. This is a catalyst, the red hot iron, and then after that it goes out. It will go into the condenser. The condenser is red hot iron, right? Red hot iron is very hot, so it has high temperature. So this catalyst of red hot iron actually is very hot. So this chamber is where it becomes NH3. After the NH3 is produced, it will go into the condenser where it will be cooled down to produce liquid ammonia. So it will go here, and then there will always be some remaining nitrogen gas and hydrogen gas, and there will also be some ammonia gas that will eventually escape. So it will go back and then start the whole process again. So again, nitrogen gas and hydrogen gas go into the compressor. They become pressured. It goes into the chamber, and the iron powder is hot, so it creates a high temperature. It turns into ammonia gas. The ammonia gas goes into the condenser, and at the condenser it turns into liquid. The liquid is collected, but not all of them are collected. Some are still a gas, while some are still hydrogen and some are still nitrogen gas. So it goes back and starts the whole process again. Okay, we're almost at the end. Okay, ammonium salts. Ammonia and ammonium are different things. Ammonium is NH4, NH4 plus. NH3 is ammonia, so you have to be careful of the difference. Ammonium salts are white. They are soluble. They decompose easily when heated. So when you were to, for example, if you were to decompose NH4H3O3, you will always get ammonia gas and some extra products. In this case, it's water and carbon dioxide. But the main product of decomposition of ammonium salts is going to be ammonia gas. I believe we just mentioned it just now. And then ammonium base plus ammonium salt will always produce ammonia gas. So there's two ways to gain ammonia gas: decomposing ammonium salts or reacting it with a base. And let me just see if we wrote anything else. But then it did right. Yeah, basically they're all similar. They all produce NH3, and the reactions of ammonium salts and bases are used in the lab to prepare ammonia gas and to test for the presence of ammonium radicals. How do you test for the presence of ammonium radicals? So what happens is, because you know it's guaranteed that ammonia gas is going to be produced, you can use this ammonia gas. You can collect this ammonia gas, and you can react it in other ways. And if you were to get I forgot what is going on after that. It's in the qualitative analysis SPM chapter. But if you were to react NH3 with something else, you will get I think it's a brown ring. I think it's the brown ring thing. So If you get a brown ring, that means it's definitely nitrogen, so it's definitely an ammonium salt. So that's how you test the presence of ammonium salt. I forgot if it's actually the brown ring, but it's something similar to that. And of course,